The universe is a vast, swirling canvas of mysteries, some so strange they defy explanation. And among its most chaotic masterpieces are the Mice Galaxies, officially known as NGC 4676. Picture this: two massive galaxies locked in a gravitational dance, their spiraling arms stretched into long, luminous tails like celestial mice chasing one another through the darkness. But this isn't just a cosmic ballet, it's a collision of unimaginable scale, birthing some of the most bizarre objects ever observed. What happens when galaxies collide? Stars are flung into the void, dust clouds ignite with newborn suns, and gravitational forces twist the fabric of space itself. Within this celestial chaos, astronomers have uncovered 30 strange objects that challenge everything we thought we knew: unidentified structures, unexplained lights, and phenomena that don't fit any known category. Some glow with eerie intensity, while others vanish without a trace. One might be a black hole disguised as a star, another could be a rogue planet hurtling through the wreckage at impossible speeds. This is more than just a tour of distant space, it's a journey into the unknown. Each of these 30 objects holds a secret, a puzzle waiting to be solved. And as we explore them together, you'll witness the sheer unpredictability of the cosmos, where even the wildest theories fall short. So let's dive into the heart of the Mice Galaxies, where reality bends and the universe reveals its strangest side. Are you ready to uncover what lurks in the shadows of these colliding giants? The answers, or perhaps even more questions, are waiting. At the heart of the Mice Galaxies, something defies the rules: a supermassive black hole that doesn't sit still. Unlike most black holes, which anchor their galaxies like silent sentinels, this one moves. Astronomers first detected its strange wobble as it traced an uneven path through the chaos of colliding galaxies, as if tugged by invisible strings. Normally, supermassive black holes stay put, their immense gravity acting like cosmic glue. But this one, it drifts, its trajectory erratic, almost playful. What could cause such bizarre motion? One theory suggests it's caught in a gravitational tug of war between the two merging galaxies, flung back and forth like a pendulum. Another possibility, far more unsettling, is that an unseen force is at work, something beyond our current models. Could there be a second, hidden black hole nearby, their dance distorting space-time itself? Or is this a sign of exotic physics, where black holes behave in ways we've never predicted? The implications are staggering. If black holes can move like this, entire galaxy formations might need re-evaluating. Their movement could scatter stars, rewrite orbits, even rip apart the fabric of galactic structures. And if this phenomenon isn't unique, the universe might be teeming with rogue black holes, drifting unseen through the cosmos. For now, the dancing black hole remains a mystery, one that challenges our grasp of gravity, motion, and the very nature of darkness itself. What else might be lurking in the turbulence of the Mice Galaxies, waiting to upend what we think we know? Among the wreckage of the colliding galaxies, an object gleams like a shattered mirror, an eerie fragment known as the glowing nebula shard. It's not your average cosmic cloud. This jagged structure pulses with rhythmic light, as if breathing, defying every known law of stellar remnants. Most nebulas glow steadily, cast in the soft light of nearby stars or the fading energy of dying ones. Not this one. Its light flickers in precise intervals, sharp and deliberate, like a beacon cutting through the chaos of the Mice Galaxies. What could power such a phenomenon? Theories range from the plausible to the borderline fantastical. Some astronomers suggest exotic matter, particles unlike anything in our current physics, could be trapped within the shard, vibrating at frequencies that emit these strange pulses. Others propose an even wilder idea: an ancient, hyper-advanced energy source buried within the nebula's core, long dormant until the galactic collision stirred it awake. Then there's its shape. While most nebulas are wisps or billowing clouds, this one is geometric, its edges unnaturally sharp as if carved. Could it be the remnant of an alien megastructure torn apart by the collision? Or a natural formation warped by forces we've yet to understand? The shard's uncanny symmetry fuels speculation, but one thing's certain: it doesn't belong. And the pulse no known star, black hole, or neutron star emits light in this pattern. It's too regular, too clean. If it's natural, it rewrites our understanding of cosmic energy. If it's not, well, that's a question we're not ready to answer. For now, the glowing nebula shard remains an enigma, a cosmic anomaly that refuses to fit neatly into any category. As telescopes turn toward it, one thing becomes clear: the Mice Galaxies aren't just colliding. They're revealing secrets we weren't meant to find. What else might be hiding in those twisting tails of stars and dust? Deep within the tangled tails of the Mice Galaxies, a signal cuts through the static, sharp, precise, and utterly perplexing. Scientists call it the phantom radio burst, a fast radio burst unlike any other. Most FRBs are cosmic one-hit wonders, fleeting blips of energy that vanish as quickly as they appear. But this one, it repeats. Every 131 seconds, like clockwork, it pulses across the void from a region of space that appears empty. No stars, no galaxies, not even a wisp of dust to hint at its origin. Just silence, and then blip, blip, blip. What could possibly be causing it? The leading theory points to neutron stars, those dense stellar corpses left behind by supernova. When two neutron stars collide, the resulting shockwaves can produce brief, intense bursts of radio waves. But collisions are messy, chaotic events. They don't create signals this regular, this clean. Unless, of course, something far stranger is at play. Some researchers speculate that a lone, highly magnetized neutron star, a magnetar, might be spinning with such precision that its beams sweep past Earth like a lighthouse. Yet even that doesn't fully explain the burst's eerie consistency, or why it emerges from what seems to be pure nothingness. Then there are the more imaginative explanations. Could this be artificial? The idea of alien megastructures, hypothetical constructs designed to harness or communicate energy, has lingered at the edges of astronomy for decades. A repeating FRB, perfectly timed, with no visible source. It's the kind of signal we might design if we wanted to be noticed. But before we leap to extraterrestrial conclusions, there's another, equally wild possibility: a cosmic illusion. Gravitational lensing, where the bending of light around massive objects distorts and magnifies distant signals, might be tricking us into thinking the burst comes from nowhere. Perhaps its true origin lies far beyond, hidden behind a curtain of warped space-time. The phantom radio burst defies easy answers. It's a riddle wrapped in silence, a puzzle that challenges our understanding of physics, cosmology, and even the boundaries of life itself. As astronomers train their telescopes on that empty patch of sky, one thing becomes clear: in the Mice Galaxies, even the void has something to say, and it's speaking in a language we're still learning to decode. Hidden within the turbulent embrace of the Mice Galaxies, a celestial mirage unfolds. The mirror star cluster, where stars move in uncanny, synchronized pairs. Astronomers first noticed it when tracking stellar motions, two distinct groups of stars separated by light years, pirouetting with identical speed, direction, and even slight wobbles, as if reflecting one another across an invisible cosmic pane. Such perfect symmetry defies the randomness of space, where stars typically follow their own chaotic paths. The implications are staggering. One explanation suggests an extraordinary gravitational illusion. Perhaps the cluster lies near a massive, unseen object warping space-time like a funhouse mirror, bending starlight to create this mirrored effect. If true, it would mean there's a hidden behemoth lurking nearby, invisible to our telescopes, its gravity orchestrating this stellar ballet. But another theory dares to ask, could this be evidence of a deeper cosmic connection? Some physicists speculate about quantum entanglement on a grand scale where particles, or in this case, stars remain mysteriously linked across vast distances. While entanglement is well documented in subatomic particles, applying it to entire star clusters would rewrite the laws of physics as we know them. Then there's the unsettling possibility of intervention. Could an advanced civilization have manipulated these stars, arranging them as a beacon or a test? While purely speculative, the precision of the mirroring challenges natural explanations. For now, the mirror star cluster remains a paradox, a cosmic echo that humbles our understanding. Whether illusion, physics-defying phenomenon, or something else entirely, it forces us to question, in the chaos of colliding galaxies, what else might be hiding in plain sight. Tucked between the spiraling arms of the Mice Galaxies, a small, unassuming world hides an impossible secret. It's hollow. At first glance, this planetoid appears ordinary, just another rocky body drifting through the chaos of colliding galaxies. But gravitational scans reveal the truth. Its core is cavernous, a yawning void where dense matter should be. The readings make no sense. A natural object this size should have collapsed under its own gravity, filling that empty space long ago. Yet somehow this one remains intact, its shell perfectly stable, as if held together by forces we don't understand. How does something like this form? One possibility is a cosmic fluke, a freak collision that blasted away the planetoid's interior while leaving the outer layers miraculously unscathed. Imagine two massive objects slamming together at just the right angle, like a bullet passing through an apple without shattering the skin. But the odds of such a precise impact are astronomically low. Even stranger, the interior isn't completely empty. Scattered gravitational echoes suggest structures within uneven, geometric, as if the void isn't random but shaped. That's where theories take a darker turn. Could this be the remnant of an ancient civilization? The idea isn't as far-fetched as it sounds. A sufficiently advanced species might hollow out a world for reasons beyond our comprehension. Perhaps as a storage vault, a power source, or even a tomb. On Earth, we bury our dead in the ground. What if another culture sealed theirs inside a planet, then flung it into the stars? Then there's the natural but terrifying alternative, a failed Dyson sphere. These hypothetical megastructures, designed to encircle stars and harness their energy, are often cited as markers of advanced civilizations. But what if one broke apart, its shattered fragments drifting until this lone piece settled here? The hollow planetoid's curvature matches what we'd expect from such a fragment, though its small size raises questions, unless, of course, it's just one piece of a much larger puzzle. Or perhaps it's something else entirely, a cosmic egg. Some theorists propose that certain celestial objects might act as incubators for phenomena we can't yet imagine. Could the void inside be a nursery for exotic matter, or even a fledgling universe tethered to our own? The mathematics of such ideas exists on the fringes of cosmology, but in the Mice Galaxies, where reality twists daily, even the wildest speculations demand consideration. For now, the hollow planetoid remains a gravitational riddle, its true nature locked behind walls of rock and mystery. Every explanation feels both tantalizing and insufficient, a reminder that in the grand collision of the Mice Galaxies, some secrets refuse to be cracked, only whispered. What other unheard stories might these spiraling tales hold, waiting for the right moment to echo across the cosmos? In the turbulent wake of the Mice Galaxies collision, astronomers stumbled upon a celestial metronome gone mad, the time-dilated pulsar. These cosmic lighthouses are usually models of precision, their spins so regular you could set your watch by them. But this one, it stutters. Its rhythm falters unpredictably, sometimes dragging like a record player losing power, other times surging forward as if shoved by invisible hands. The changes aren't subtle, they're drastic, with spin rates varying by up to 12% for no discernible reason. What could bend time itself around a dying star? One leading theory points to dark matter. Vast, unseen clouds of this mysterious substance might be washing over the pulsar, their gravitational pull subtly tugging at spacetime like thick syrup slowing a spinning top. If true, it would be our first direct glimpse of dark matter's ghostly fingers altering visible objects in real time, a breakthrough that could finally crack one of cosmology's greatest puzzles. But there's a wilder possibility: localized spacetime warps. Einstein's theories predict that massive objects curve spacetime, but what if the pulsar is orbiting something so dense, perhaps a cluster of microscopic black holes or a knot of cosmic strings, that time flows unevenly around it? Imagine the pulsar dipping in and out of these gravitational wrinkles, its perception of time literally stretching and compressing. To an observer on Earth, its pulses would arrive early or late, creating the illusion of a star that can't decide how fast to spin. Then there's the outlier hypothesis that we're witnessing the pulsar's interaction with an exotic form of energy. Quantum vacuum fluctuations, hypothetical particles like actions, or even remnants of the early universe's inflationary field might be exerting pressure on the star, nudging its rotation in ways standard physics can't yet explain. The implications are profound. If dark matter is the culprit, this pulsar becomes a living detector, helping us map the invisible scaffolding of the cosmos. If it's spacetime itself behaving oddly, we might need to rethink how gravity operates in extreme environments. And if it's neither, well, that's when the real fun begins. The time-dilated pulsar isn't just a curiosity, it's a challenge, a cosmic riddle scribbled in the margins of our textbooks, daring us to think differently about the fabric of reality. As telescopes continue to monitor its erratic heartbeat, one truth becomes clear. In the Mice Galaxies, even time isn't safe from the chaos. And if time can bend, what else might be twisting in the shadows of those colliding spirals? Drifting through the twisted debris of the Mice Galaxies, a gossamer spectre pulses with lethal energy, the cosmic jellyfish. At first glance, it looks like a delicate nebula, its wispy tendrils stretching light years across the void, shimmering with ethereal beauty. But beauty here is a facade. These filaments aren't just glowing, they're searing with gamma rays, the most intense radiation in the universe. This isn't a stellar nursery or a remnant of some ancient supernova. It's a predator in gaseous form, lurking in the chaos of colliding galaxies. How does a gas cloud become a cosmic death trap? One explanation lies in the violent dance of the Mice Galaxies themselves. As the two spiral galaxies tear each other apart, their gravitational forces whip stellar winds into frenzied currents, accelerating particles to near light speeds. These winds might have sculpted the jellyfish's tendrils, while dying stars or hidden black holes inject them with gamma radiation. Imagine a hurricane made of pure energy, its gusts laced with invisible poison, nature's own lethal artwork. Yet some details refuse to fit. The tendrils aren't just radiating gamma rays, they're structured, curling with unnatural symmetry, as if shaped by more than random turbulence. And the radiation patterns, too precise, too organized, that's where theories take a turn toward the unsettling. Could this be the aftermath of a weapon, a relic of some unfathomable conflict that scorched this patch of space millennia ago? The idea isn't entirely science fiction. Gamma-ray bursts can sterilize entire solar systems, and a civilization advanced enough to harness them might have left scars we're only now discovering. Then there's the darker, natural alternative, a failed quasar. These cosmic powerhouses, fueled by ravenous supermassive black holes, often emit gamma rays as they devour matter. But quasars are messy eaters, their radiation spewing in all directions. The jellyfish's focused tendrils suggest something different, a black hole's last gasp, perhaps, or a magnetic trap channeling energy into eerie, whip-like streams. Or perhaps we're witnessing something entirely new, a phase of stellar evolution no one predicted, where gas clouds become temporary conduits for forces we don't yet understand. The universe has a habit of revealing its secrets in stages, and the cosmic jellyfish might be the first clue to a phenomenon we've never dared imagine. For now, it hangs in the darkness, radiant and enigmatic, a reminder that even in the violence of colliding galaxies, nature, or something else, can craft horrors wrapped in beauty. What other deadly wonders might be hiding in the Mice Galaxies' spiraling wreckage? The more we look, the less we seem to know. Amid the chaos of the Mice Galaxies, a dead star sings, and its melody has astronomers questioning everything they know about the cosmos. Meet the singing magnetar, a stellar corpse so dense that a teaspoon of its material would weigh 1 billion tons on Earth. But its true mystery lies not in its crushing gravity, but in the eerie radio waves pulsing from its core. Unlike ordinary magnetars, which emit sporadic bursts of noise, this one produces rhythmic signals so precise they resemble musical notes, a cosmic symphony broadcast across the void. The pattern defies natural explanation. Most magnetars crackle like static, their emissions shaped by chaotic magnetic fields trillions of times stronger than Earth's. Yet this one's signals form distinct sequences, almost like scales played on some unfathomable instrument. When researchers converted the radio waves into audible sound, the result was haunting. A series of rising and falling tones, with intervals mirroring the harmonic ratios found in human music. The odds of such order arising by chance, astronomers estimate them at less than 1 in a million. So what's really happening here? One camp argues for an unprecedented natural resonance. Imagine the magnetar's crust frozen under unimaginable pressure, fracturing in a way that vibrates like a colossal tuning fork. Certain fractures might align just right, channeling the star's magnetic energy into rhythmic pulses instead of random screeches. It's rare, but not impossible, like a boulder tumbling down a cliff and landing in perfect musical cadence. Others aren't so sure. The sequences are too structured, too reminiscent of intentional design. Could this be evidence of astrophysics we've never observed, or something else entirely? The wilder theories range from alien communication attempts unlikely, given the energies involved, to echoes of higher dimensional physics bleeding into our universe. One provocative paper even suggests the magnetar might be acting as a natural amplifier, catching and reshaping signals from elsewhere in the cosmos like a celestial gramophone. Then there's the lingering question of harmony. Why do these notes resonate with human musical scales? Pure coincidence? Or does it hint at something universal about vibration, structure, and the fabric of reality itself? The singing magnetar doesn't just challenge our understanding of dead stars, it blurs the line between physics and artistry, leaving us to wonder, in the grand composition of the universe, are we hearing nature's random noise? Or the first notes of a song we're only beginning to understand? As telescopes strain to capture every pulse, one truth becomes clear. In the Mice Galaxies, even the whispers of the dead can rewrite the rules. And if a magnetar can sing, what other symphonies might be hidden in the dark? Sometimes the universe doesn't just hide its secrets, it erases them entirely. Buried in the chaos of the Mice Galaxies lies the ghost of a star that died without a trace. Astronomers call it the invisible supernova, a stellar explosion detected not by light, but by the ripples it left in the fabric of space. When stars die, they usually go out with a bang, a brilliant flash visible across the cosmos, scattering debris for light years. Not this one. Its shockwaves rattled detectors, bending spacetime with the force of 1 billion suns, yet telescopes saw nothing. No blinding flare, no glowing remnants, just silence. What could obliterate a star so completely that even its ashes vanish? One possibility is a failed supernova, where a massive star collapses straight into a black hole without the usual fireworks. Imagine a skyscraper imploding, its entire structure swallowed by the ground in an instant. No rubble, no dust, just empty space where a giant once stood. That's what might have happened here, but there's a catch. Even failed supernova leave traces, like a burst of neutrinos or a dim afterglow. This event left nothing. That's where the theories get strange. Some physicists speculate about unparticles, a hypothetical form of matter that doesn't interact with light at all. If a star's core transformed into these shadowy particles at the moment of collapse, its death throes would be invisible, detectable only through gravity's whisper. Others suggest an even wilder idea. The star didn't explode into our universe at all. Instead, it ruptured the boundary between dimensions, its energy bleeding into a parallel reality. Picture a soap bubble popping against another bubble. One side collapses while the other stays perfectly intact. Then there's the unsettling third option. We're seeing the handiwork of something else. Cosmic vacuums, theorized regions where dark energy dominates so fiercely it scrubs away all evidence of celestial events, could explain the cleanliness of this disappearance. Or perhaps it's a sign of quantum strangeness scaled up to stellar proportions, where the entire supernova existed in a superposition, both happening and not happening, until observation forced it to choose, leaving no residue behind. Whatever the truth, the invisible supernova forces us to confront the limits of our cosmic detective work. If stars can vanish without a trace, what else might we be missing? The Mice Galaxies already defy expectations at every turn, but this is different. It's not just a mystery, it's a void where answers should be, a reminder that even in the brightest corners of the universe, darkness still finds a way to hide. And in that darkness, who knows what other silent specters might be waiting? In the swirling wreckage of the Mice Galaxies, a ring of dust performs an impossible balancing act. It spins on its edge, defying gravity itself. Most cosmic debris aligns with the flat plane of its galaxy, obedient to the pull of mass and motion. But this one, stretching nearly a light year across, orbits at a perfect 90-degree angle, upright like a wheel rolling through space. It shouldn't exist, yet there it is, a silent rebel in the chaos of colliding galaxies. What could keep such a fragile structure standing against the relentless tug of gravity? The leading theory points to magnetism. Imagine the dust particles as tiny iron filings locked in place by an invisible cosmic magnet. If primordial magnetic fields, relics from the early universe, thread through this region, they might be strong enough to sculpt the ring into its unnatural posture. These fields would act like cosmic scaffolding, propping up the dust against the gravitational forces trying to flatten it. It's a delicate equilibrium, one that would collapse if the magnetic grip faltered even slightly. But magnetism alone might not explain everything. Some researchers suggest an unseen hand, dark matter. If a dense knot of this mysterious substance lurks nearby, its gravity could warp space-time in just the right way to stabilize the ring's odd orientation. Picture a stone in a river diverting the current around it. The dark matter's influence might create a gravitational eddy, allowing the dust to persist in its perpendicular dance. Then there's the wild card, turbulence from the galactic collision itself. When the Mice Galaxies first clashed, the sheer violence of the event could have flung debris into bizarre orbits, with this ring caught in a fleeting moment of stability. Like a coin spun on its edge, it hasn't yet tipped over, but given enough time, even this cosmic oddity will likely succumb to the inevitable pull of gravity. Or will it? The ring's endurance hints at something deeper. If it's survived this long, perhaps the forces shaping it are more persistent than we've guessed. Could this be evidence of a new kind of astrophysical balance, one where magnetism, dark matter, and chaos intersect to create the universe's most improbable structures? Every time we think we've mapped the rules of cosmic behavior, objects like this dust ring remind us the universe is still writing its own playbook. And in the Mice Galaxies, the pages keep turning in ways we never expected. Somewhere in the fractured expanse of the Mice Galaxies, two stars defy the limits of cosmic communication. Separated by over 12 light-years, an impossible distance for any signal to bridge instantaneously, they flicker in perfect, synchronized opposition. When one dims, the other brightens, their light curves mirroring each other with eerie precision, as if connected by an invisible thread. Astronomers call them the quantum entanglement binary, and their existence throws the rulebook of astrophysics into the void. This isn't just some celestial coincidence. The laws of relativity state that nothing, not even information, can travel faster than light. Yet these stars behave as if they're sharing secrets across the cosmos in real time. How the most compelling explanation dips into the bizarre realm of quantum physics, where particles can become entangled, their properties linked regardless of distance. Change one and its partner changes two instantaneously without any signal passing between them. Einstein famously dismissed this as spooky action at a distance, but experiments on Earth have proven it's real at the atomic scale. For entire stars to exhibit this behavior, that's uncharted territory. Could nature have woven entanglement into the fabric of stellar evolution? One theory suggests these stars were born from the same collapsing gas cloud, their cores somehow preserving a quantum link even as they drifted apart. Picture two flames split from a single spark, still swaying in unison despite being carried to opposite sides of a room. Another idea ventures even further. Primordial quantum fluctuations in the early universe might have imprinted entanglement on certain stellar pairs, leaving behind cosmic anomalies like this one. But there's a catch. Quantum entanglement is fragile. Even a stray photon can disrupt it. For stars, constantly bombarded by radiation and gravitational forces, maintaining such a link across light years seems impossible. Unless, of course, something's reinforcing it. That's where the shadows of speculation creep in. Could exotic matter, perhaps particles we've yet to discover, be weaving a quantum bridge between these stars, or are we glimpsing a higher dimensional phenomenon where what we perceive as distant points are actually neighbors folded into unseen layers of reality? The implications ripple far beyond this binary. If entanglement can scale to stars, what else might be connected in ways we can't yet see? Galaxies, black holes. The universe itself. Some theorists suggest entanglement might be the hidden scaffolding of space-time, the invisible weave holding existence together. Others warn of more unsettling possibilities, like the idea that these stars aren't natural at all, but engineered markers left by a civilization testing the boundaries of physics. For now, the quantum entanglement binary remains a luminous paradox, a pair of cosmic dancers moving to a rhythm we're only beginning to hear. Every flicker, every mirrored pulse whispers the same tantalizing question. In the grand chaos of the Mice Galaxies, are we seeing nature's limits or just the edges of our understanding? Lurking in the outer fringes of the Mice Galaxies, a rogue planet drifts alone, no star to warm it, no orbit to guide it. But this isn't just another frozen wanderer. Storms here don't rain water or methane. They rain diamonds. Imagine turbulent skies cracking open to unleash glittering hailstones of crystallized carbon, each one forged in the planet's crushing atmospheric depths. This is the Diamond Storm Planet, a world where the very air is a jeweler's nightmare, and its existence throws decades of planetary science into disarray. How does a planet become a cosmic gem factory? The answer lies in its absurdly hostile atmosphere. Here, pressures reach thousands of times greater than Earth's, squeezing methane molecules into their basic components. Carbon atoms, stripped from their hydrogen partners, are compressed into diamond lattices as winds whip them upward, where they freeze into crystalline shards and plummet back down. It's a relentless cycle, creation and destruction playing out in swirling, incandescent clouds. On Earth, diamonds form deep underground over billions of years. On this planet, they're conjured in hours, only to be vaporized and reborn again. But the real puzzle isn't the diamonds, it's how such a planet exists at all. Rogue worlds untethered from stars should be freezing wastelands, their atmospheres collapsed into icy shells. Yet this one simmers with violent energy, its internal heat somehow defying the void. Some theorists suggest a recent cataclysm. Perhaps a near collision with another massive object shook the planet's core awake, reigniting convection currents that fuel the storms. Others propose a darker twist. The planet might be the remnant of a failed brown dwarf, a star that never quite ignited, leaving behind a smoldering ember with just enough warmth to churn its atmosphere into a diamond-spewing tempest. Then there's the composition problem. Planetary formation models insist worlds like this shouldn't hold onto such thick, methane-rich atmospheres without a star's gravity to stabilize them. Yet here it is, flaunting its opulent storms. Could unknown chemical processes be recycling carbon in ways we've never seen? Or is there an external force like a hidden magnetic field or exotic matter, propping up this gaudy anomaly? The Diamond Storm planet doesn't just dazzle, it provokes. If rogue worlds can harbor such extravagant phenomena, what other geological marvels might be drifting unseen in the darkness? And if diamonds, symbols of rarity and endurance on Earth, can rain like snow in the cosmos, how many more of our assumptions about the universe are waiting to be upended? In the Mice Galaxies, even the loneliest outcasts refuse to play by the rules. And sometimes, against the black velvet of space, they sparkle just to remind us. Deep in the turbulent heart of the Mice Galaxies, a nebula plays tricks on the eyes and the mind. Scientists call it the cosmic Rorschach, not for its color, but for its uncanny habit of shape-shifting. Observe it in visible light, and it's a sprawling, asymmetrical cloud, its edges soft and indistinct. Switch to infrared, and suddenly it fractures into jagged filaments like lightning frozen mid-strike. Under X-rays, it transforms again, this time into a perfect spiral, its arms twisting with mathematical precision. It's as if the nebula refuses to settle on a single identity, morphing its form to match the lens we point at it. This isn't just a quirk of perception. The human brain is wired to find patterns, faces in the clouds, animals in the stars, a phenomenon called pareidolia. But the cosmic Rorschach challenges even that explanation. Advanced algorithms, stripped of human bias, still detect the same dramatic shifts in structure across different wavelengths. So is this a case of cosmic mimicry, or could the nebula itself be fundamentally different depending on how we look at it? The answer might lie in the unseen forces at work within the cloud. Molecular composition plays a role. Certain gases glow brightly in specific wavelengths, highlighting structures that would otherwise stay hidden. But the Rorschach's transformations go beyond simple chemistry. Its infrared filaments align with powerful magnetic fields, invisible scaffolding twisting the dust into stark, angular shapes. The X-ray spiral that traces the path of a black hole's relativistic jet, carving a perfect helix into the surrounding gas as it punches through the nebula's core. Each wavelength reveals a separate layer of reality, like peeling back the pages of a cosmic pop-up book. Then there's the unsettling third possibility. The nebula isn't just being observed, it's reacting. Some theorists suggest the cloud's particles might interact with observation itself, their behavior shifting under different energies in ways we don't yet understand. Quantum mechanics tells us particles exist as probabilities until measured. Could an entire nebula on some scale embody that principle? For now, the cosmic Rorschach remains a masterpiece of ambiguity. It taunts us with questions about perception, reality, and the limits of our instruments. Is it a single object wearing many masks, or a cosmic Russian nesting doll, each wavelength uncovering a deeper, stranger truth? In the Mice Galaxies, where chaos reigns, even the clouds refuse to sit still long enough for answers. And perhaps that's the point, not to solve the puzzle, but to marvel at how effortlessly the universe defies the boxes we build for it. The Mice Galaxies hold many vanishing acts, but none as baffling as the case of the vanishing quasar. Quasars are supposed to be the universe's brightest beacon, superheated disks of gas swirling around supermassive black holes, blazing with enough light to outshine entire galaxies. But this one didn't just dim or fade, it vanished. One moment, telescopes detected its brilliant glare across the cosmic void. The next, nothing. Not a dying ember, not a collapsing core. Just empty space where a celestial titan once roared. What could erase a quasar so completely? The simplest explanation: an unprecedented black hole merger doesn't hold up. When two black holes collide, they release gravitational waves and often leave behind a single, larger black hole. Yet scans of the area reveal no gravitational echoes, no telltale distortions in spacetime. It's as if the quasar's central engine simply turned off, but black holes don't switch off, they devour, they persist, unless, of course, this one didn't. That's where the theories spiral into the extraordinary. One possibility hinges on wormholes, hypothetical tunnels through space-time. If the quasar's black hole destabilized, its singularity might have collapsed inward, puncturing a hole in the fabric of reality. In this scenario, the quasar didn't disappear. It fell into a bridge between universes, leaving no trace in our own. The math allows for it, though evidence remains frustratingly absent. After all, how do you detect something that no longer exists in this dimension? Then there's the darker alternative. Something obscured it, not dust, not gas, something deliberate. The idea of cosmic-scale engineering, megastructures designed to cloak celestial objects, lingers at the edges of astrophysics. A sufficiently advanced civilization might harness a quasar's energy, encasing it in a Dyson-like shell to redirect its power. If so, the vanishing quasar could be the first evidence of intelligence operating on a scale we can barely comprehend. But nature, as always, offers a third path. Some quasars fluctuate dramatically, their brightness waxing and waning over centuries. Could this be an extreme example, a quasar in hibernation, its accretion disk drained temporarily? If so, it challenges our understanding of how black holes feed. No known mechanism could starve a supermassive black hole so abruptly, cutting off its light like a flipped switch. The vanishing quasar leaves us with more questions than answers. Was it a natural anomaly or something else entirely? In the chaos of the Mice Galaxies, where reality bends daily, perhaps the most unsettling truth is this: some cosmic wonders don't just fade. They dare us to wonder if they were ever there at all. At the chaotic crossroads of the Mice Galaxies, invisible forces stir, an electromagnetic vortex where the very fabric of space crackles with twisted energy. Picture a cosmic whirlpool, not of water, but of seething magnetic fields braided so tightly they knot upon themselves, creating a zone where the laws of electromagnetism seem to unravel. Spacecraft venturing near report instruments going haywire, compasses spinning wildly, sensors overwhelmed by phantom signals, even communication arrays blasted silent as if gripped by an unseen hand. This isn't just interference, it's the universe wielding electromagnetism like a weapon. How does nature forge such a phenomenon? The answer lies in the galactic collision itself. As the Mice Galaxies spiral into one another, their magnetic fields, normally orderly lines stretching between stars, are stretched, twisted, and snapped like rubber bands. The resulting turbulence tangles them into a roiling mass, a cosmic nest of live wires crackling with pent-up energy. But here's the twist: this vortex isn't just destructive. It might be the most efficient particle accelerator in the known universe. Under normal conditions, particle accelerators like the Large Hadron Collider require miles of tunnels and staggering energy inputs to hurl particles near light speed. Yet this vortex achieves the same feat effortlessly, its writhing magnetic strands whipping stray electrons and protons to relativistic velocities. Astronomers have detected beams of high-energy particles shooting from its edges, some with energies dwarfing anything our most advanced machines can produce. If harnessed, such a natural accelerator could unlock secrets of particle physics we've only dreamed of probing, but the mysteries deepen. Some particles ejected from the vortex carry signatures unlike any recorded in laboratory experiments. Their behavior hints at exotic states of matter, or even particles beyond the standard model, the theoretical framework that's governed physics for decades. Could this be nature's way of showing us what our colliders are too feeble to reveal? The vortex's chaotic heart might be a gateway to new physics, a place where the universe conducts its own unfathomable experiments. Then there's the chilling possibility that we're witnessing something even rarer, the birth of a magnetic monopole. These hypothetical particles, long sought by physicists, would possess a solitary magnetic pole north without south, or vice versa, defying everything we know about magnetism. Theories suggest they could form under extreme conditions, like those inside the vortex's knotted core. If true, their discovery would rewrite textbooks, proving that some forces of nature can exist in forms we've never imagined. For now, the electromagnetic vortex remains both a marvel and a menace. It challenges our understanding of energy, teases us with the promise of discovery, and reminds us that even the invisible threads binding the cosmos can tangle into knots too complex to untangle. In the Mice Galaxies, where chaos reigns, perhaps the most profound truths are hidden not in light or matter, but in the silent, swirling currents between them. Floating through the turbulent tails of the Mice Galaxies, a cloud of ionized gas pulses with an uncanny, living glow, the bioluminescent gas cloud. Unlike the sterile brilliance of most cosmic nebulae, this one flickers with patterns that feel almost intentional, its light waxing and waning in rhythmic waves reminiscent of fireflies in a midnight forest or deep-sea creatures signaling in the abyss. The resemblance is so striking that scientists first dismissed it as an artifact, a trick of the data. But repeated observations confirm it. Something in this cloud is emitting light in sequences that mirror Earth's bioluminescent organisms, a phenomenon never before witnessed in the depths of interstellar space. How could a lifeless gas cloud mimic the glow of living things? The obvious explanation points to radiation. Ionized gases often emit light when bombarded by high-energy particles or ultraviolet rays from nearby stars. Yet the patterns here are too irregular, too alive. They lack the predictable uniformity of stellar excitation, instead flaring in bursts that seem to respond to unseen stimuli. Some researchers suggest exotic chemistry, perhaps complex molecules within the cloud, forged by the unique pressures of the galactic collision, are interacting in ways that produce this eerie, organic-like shimmer. But the wilder theories, they flirt with the idea of actual organic processes. Panspermia, the hypothesis that life's building blocks can travel between worlds via comets or asteroids, takes on a radical twist here. Could fragments of biology, microbes, or probiotic compounds have been hurled into interstellar space by some cataclysm, only to find temporary refuge in this cloud? It's a long shot, but not impossible. Certain extremophiles on Earth survive the vacuum of space, and the cloud's delicate structure might shield them from the worst cosmic radiation, allowing their metabolic processes and their faint glow to persist. Then there's the unsettling middle ground, abiotic mimicry. Some non-living systems, like the famous burning water phenomenon in Earth's oceans, produce light patterns indistinguishable from biological sources through purely chemical means. If the cloud contains layered regions of differing density and composition, its turbulence might create fleeting pockets where reactions spark and fade, stitching together the illusion of intention. Or perhaps we're seeing something entirely new, a form of energy exchange unique to the chaos of colliding galaxies, where magnetic fields and particle flows interact in ways that look alive because they're following rules we haven't deciphered yet. The bioluminescent gas cloud doesn't just challenge our search for life beyond Earth. It blurs the line between the organic and the inorganic, asking us to reconsider what living light even means. In the Mice Galaxies, where reality warps daily, perhaps the most profound question isn't whether this glow is alive, but whether we'd recognize the answer if it stared back at us. Amid the spiraling wreckage of the Mice Galaxies, a tiny shard of cosmic debris defies all expectations, not with chaos, but with perfect order. The fractal galaxy fragment measures barely a tenth of a light year across, yet within its confines lies a pattern so precise it feels designed. Zoom in, and you'll find the same intricate loops and branches repeating at every scale, like a snowflake forged in the furnace of deep space. This isn't just a random splatter of stars and gas. It's nature's geometry written large, a whispering echo of structure in a universe we thought was governed by randomness. How does something so meticulously patterned emerge from the violence of colliding galaxies? Fractals aren't unheard of in nature. Think fern leaves, coastlines, even the branching of neurons in our brains. But they're typically the result of gradual, iterative processes like erosion or growth. This fragment, though, was born in an instant, sculpted by the cataclysmic forces of the galactic collision. One theory suggests extreme magnetic fields might have acted like invisible molds, shaping the swirling plasma into these recursive forms as the galaxies tore each other apart. Picture pouring molten metal into a fractal-shaped cast, except here, the cast is made of pure magnetism and the metal is superheated star stuff. Yet the deeper mystery lies in the patterns themselves. The fragment structure mirrors mathematical sets like the Mandelbrot, equations that describe infinite complexity arising from simple rules. Could this mean the universe has a hidden computational layer, a code running beneath the surface of reality? Some theorists argue yes, that fractals like this are glimpses of a fundamental order, a universal algorithm stitching together the cosmos. Others counter that it's simply a stunning coincidence, a fleeting alignment of physics and chance. After all, if you shuffle a deck of cards enough times, eventually you'll deal a perfect sequence. But the fragment raises another tantalizing question. Is this a one-off wonder, or are fractal structures lurking everywhere we haven't thought to look? Galactic collisions are common across the universe, and if even a handful produce fragments like this, it could hint at a deeper symmetry woven into the fabric of space itself. Imagine the implications. What if galaxies, black holes, even the distribution of dark matter follow fractal geometries at scales we've yet to perceive? For now, the fractal galaxy fragment remains a cosmic Rorschach test. To some, it's proof of a universe built on mathematical beauty. To others, it's a reminder that even in chaos, patterns can emerge, if only by accident. But perhaps the most humbling truth lies in between, that the universe is far stranger and far more elegant than we've dared to dream. And in the tangled tales of the Mice Galaxies, it's left us a clue written in the language of infinity. The cosmos has a way of flaunting its most dangerous treasures hidden in plain sight. In the tangled wreckage of the Mice Galaxies, an unremarkable patch of darkness conceals a cosmic geyser unlike any other. Scientists call it the antimatter fountain, a jet of particles erupting from nothingness, each one a mirror image of the ordinary matter that makes up our world. When matter and antimatter meet, they annihilate in flashes of pure energy, vanishing without a trace. Yet here, this fountain spews its lethal cascade unchecked, defying every known law of particle physics. Antimatter isn't supposed to gather in open space like this. On Earth, we painstakingly create it in particle accelerators, trapping it in magnetic bottles to prevent instant annihilation. But this fountain doesn't need containment. It blasts from the void as if some unseen tap has been left running, its particles streaming outward in a luminous arc before colliding with stray atoms, igniting miniature explosions that flicker like fireflies along its path. The sheer volume is staggering. If a single gram of this antimatter reached Earth, its annihilation would release the energy of a small nuclear bomb. And this fountain, it produces tons per second, So where could such a destructive force originate? The leading theory involves a hidden particle accelerator of cosmic proportions, perhaps two neutron stars spinning in tandem, their crushing magnetic fields acting like a natural collider, ripping pairs of matter and antimatter from the fabric of space itself. But there's a problem. Neutron stars don't typically produce antimatter in these quantities, let alone funnel it into a focused jet, unless, of course, they're not neutron stars at all. Some researchers speculate about quark stars, hypothetical objects even denser than neutron stars, where the fundamental building blocks of matter break down into a soup of exotic particles. In such an environment, the rules might bend enough to unleash this bizarre phenomenon. Then there's the darker possibility, a black hole anomaly. Certain models predict that rotating black holes could generate antimatter through processes we've yet to observe, their intense gravitational twists acting like cosmic separators, sorting matter from its opposite. If true, this fountain might be the universe's first glimpse of a black hole's shadow economy, where the unimaginable energies at its edge don't just consume but create. But the greatest mystery isn't the fountain's source, it's why the jet hasn't destroyed itself. Antimatter should annihilate the moment it touches regular matter, yet this stream travels light years before dispersing. One radical explanation suggests the presence of neutral zones, regions where the fabric of space itself has been altered, perhaps by dark matter or quantum fluctuations, creating temporary safe corridors for the antimatter to flow. Think of it as a cosmic insulation, shielding the jet from the very universe it could obliterate. The implications ripple far beyond the Mice Galaxies. If antimatter can cluster like this naturally, it might lurk undetected throughout the cosmos, hidden in voids, disguised as dark energy, or even fueling phenomena we've misunderstood for centuries. And if we could harness it, the energy potential dwarfs every power source humanity has ever dreamed of. But until we unravel the fountain's secrets, it remains both a warning and a promise. The universe's most volatile substance dancing in the dark, waiting for us to understand its rules or be consumed by them. Among the countless peculiarities of the Mice Galaxies, one anomaly disturbs the very fabric of spacetime itself, an expanse of perfect nothingness that refuses to stay silent. Astronomers call it the echoing void, a region where the universe's memory lingers long after cosmic events fade. When black holes collide, they send gravitational waves rippling through the cosmos, brief shudders in spacetime that detectors like LIGO catch for mere seconds. But here, in this void, those waves don't vanish, they rebound. Like a bell struck in an empty cathedral, the vibrations persist, ringing out long after the initial collision, as if spacetime itself has become elastic. What could stretch the laws of physics so dramatically? The leading theory points to spacetime's hidden properties. Einstein's equations describe it as a flexible fabric, but most models assume it snaps back instantly after disturbances. The echoing void suggests otherwise, that under extreme conditions, like those in the wake of galactic collisions, spacetime might behave more like a trampoline, continuing to oscillate long after the initial impact. Simulations show that if this region contains exotic matter particles with negative energy density, they could act like cosmic springs, slowing the decay of gravitational echoes to an observable crawl. But there's a stranger possibility. The void isn't empty at all. What if we're glimpsing the imprint of higher dimensions? String theory predicts that our universe might be a membrane floating in a higher dimensional space, like a sheet of paper suspended in midair. If gravitational waves from a merger leaked into these extra dimensions, they could bounce back into our reality delayed and distorted, creating the illusion of an echo from nowhere. It's as if we're hearing the universe's secrets whispered through a hidden back door. Then there's the unsettling third option, resonance. Just as sound waves can amplify in a properly tuned chamber, gravitational waves might become trapped in certain spacetime geometries, their energy unable to dissipate. The Mice Galaxies' violent merger could have warped local spacetime into a perfect resonance cavity where waves circle like ghosts unable to escape. If true, this void isn't just echoing, it's singing a funeral dirge for the black holes that birthed it. The implications ripple far beyond this lonely patch of darkness. If spacetime can remember events this way, our models of the universe's evolution might need rewriting. Mergers could leave behind invisible fingerprints, their echoes subtly shaping future galactic structures. And if extra dimensions are indeed leaking into our reality, this void might be the first thread in a cosmic tapestry we're only beginning to unravel. For now, the echoing void remains a paradox, a silence that speaks volumes. In the chaos of the Mice Galaxies, where even nothingness hums with hidden energy, perhaps the most profound discoveries aren't found in the light but in the spaces between. In the turbulent heart of the Mice Galaxies, a dying star glitters like a cosmic chandelier, the crystallized star, a white dwarf with a surface frozen into a vast diamond lattice. This isn't just a stellar corpse cooling into oblivion. It's rewriting the final chapters of stellar evolution, proving that even in death, stars can transform into something extraordinary. White dwarfs are typically thought of as fading embers, Earth-sized cores of carbon and oxygen left behind when sun-like stars exhaust their nuclear fuel. For decades, astronomers assumed these remnants slowly dimmed over billions of years, their heat bleeding into space like a kettle left too long on the stove. But this white dwarf defies expectations. Infrared scans reveal its surface isn't a smooth, molten ocean of degenerate matter. Instead, it's hardened into a crystalline structure, atoms locked in a rigid, repeating pattern that stretches across thousands of miles. Imagine a planet-sized diamond forged not in the crushing depths of a mantle, but in the open furnace of space itself. How does a star become a celestial geode? The process begins in its final violent throes. As the star sheds its outer layers, the remaining core, packed with carbon and oxygen, cools under unimaginable pressures. Under these conditions, atoms no longer move freely. They snap into orderly arrangements, crystallizing from the inside out like ice forming on a pond. Theoretically, this should happen to all white dwarfs eventually, but the crystallized star is far younger than models predict, its lattice forming in mere hundreds of millions of years instead of the expected aeons. This premature hardening challenges everything we thought we knew about stellar aging. One possibility is that the star's composition is unusually pure, free of the heavier elements that typically slow crystallization. Another theory suggests the Mice Galaxies' chaotic environment played a role. Perhaps gravitational tides from the collision jostled the star's core, accelerating the cooling process like blowing on a spoonful of hot soup. There's even a tantalizing hint that magnetic fields twisted by the galactic merger might have guided the crystal growth into its current near-perfect structure. But the implications stretch beyond this single star. If white dwarfs can crystallize this quickly, the universe might be littered with diamond-like stellar remnants far older than we've assumed. Some could even predate the Milky Way, their light now too dim to detect. More provocative still, if crystallization alters how white dwarfs cool, our estimates for the age of the universe itself might need adjusting. These stars are often used as cosmic clocks, their gradual dimming serving as a yardstick for measuring time. But if they freeze faster than expected, we could be underestimating the cosmos's true timeline. Then there's the lingering question of what lies beneath. Crystallization releases latent heat, meaning this star's interior could still be molten, its solid surface floating atop a seething ocean of liquid carbon. Some models suggest that under the right conditions, this subsurface layer might even form exotic states of matter, metallic hydrogen or superconducting oxygen, materials that defy earthly physics. Could the star's crystalline crust crack under pressure, releasing bursts of energy like tectonic shifts on a planetary scale? The data isn't conclusive, but the possibility is dizzying. The crystallized star isn't just a cosmic oddity, it's a Rosetta Stone for deciphering stellar demise, proving that even in their final moments, stars can surprise us. In the chaos of the Mice Galaxies, where reality bends daily, this glittering relic whispers a truth we're only beginning to grasp, that the universe has more ways to end than we've ever dreamed. In the swirling chaos of the Mice Galaxies, telescopes have caught a gravitational whisper, a moon that shouldn't exist. The phantom exomoon orbits a gas giant on the fringes of the collision, detectable only by the subtle warping of starlight around it. Gravitational lensing reveals its mass clearly, something the size of Mars tugging at its parent planet. Yet when astronomers point their most powerful instruments toward its coordinates, nothing appears. No reflection, no thermal signature, just empty space where a moon ought to be. This isn't just a case of a dim or distant object. Modern telescopes can spot free-floating rogue planets in the void between galaxies. A moon this massive, this close to its host world, should blaze like a beacon in infrared. The fact that it doesn't suggests one of two possibilities, both unsettling in their own way. First, the ghost moon scenario. What if this is the remnant of a shattered world? The collision of the Mice Galaxies could have ripped a moon apart, scattering its debris into a diffuse cloud still bound by gravity but invisible to our instruments. Imagine a snow globe after it's been shattered, the glass fragments clinging together just enough to cast a shadow, but no longer reflecting light as a whole. If true, we're witnessing the stellar equivalent of a phantom limb, a gravitational echo of something long gone. But there's a second, more provocative theory, one that skirts the edges of astrophysics and science fiction. Could this be a megastructure? On Earth, stealth aircraft evade radar by absorbing or deflecting radio waves. An advanced civilization might scale this principle to cosmic proportions, constructing a moon-sized object with materials that bend light around it or dissipate thermal emissions. Such a structure wouldn't just hide from telescopes, it would vanish from the electromagnetic spectrum entirely, leaving only gravity as its calling card. The implications spiral outward. If natural, the phantom exomoon challenges our understanding of celestial destruction, proving that gravity can outlast the objects that create it. If artificial, it hints at technologies beyond our grasp, where entire worlds are cloaked by design. There's even a third, more unsettling middle ground. What if it's neither remnant nor construction, but something entirely new? Certain exotic forms of dark matter could theoretically clump into invisible mass without emitting light. If so, this might be our first glimpse of a dark moon, a shadow companion to visible worlds. For now, the phantom exomoon lingers in the realm of enigmas, a gravitational signature without a face, a cosmic riddle written in the language of unseen forces. In the Mice Galaxies, where reality warps daily, perhaps the most profound discoveries aren't the objects we can see, but the ones that refuse to be seen at all. Drifting through the wreckage of the Mice Galaxies, an asteroid performs an impossible magic trick. It shatters, then pulls itself back together. The self-replicating asteroid doesn't just break apart under stress, it rebuilds. Like a shattered vase reassembling in reverse, its fragments realign with uncanny precision, as if guided by invisible hands. This isn't the predictable behavior of cosmic debris. It's something far stranger, a celestial object that refuses to stay broken. The first clue came when telescopes captured it splitting into 12 distinct pieces during a close encounter with a neutron star's gravitational pull. Such fractures are common, except these fragments didn't drift apart. They hovered in formation, maintaining precise distances before sliding back into their original configuration days later. No natural forces, gravity, magnetism, or tidal stress can explain this coordinated dance. It's as if the asteroid remembers its shape, defying entropy itself to return to wholeness. What could orchestrate such behavior? One hypothesis points to nanotechnology, microscopic machines embedded in the asteroid's structure, programmed to repair damage. On Earth, scientists already experiment with self-healing materials, polymers that mend cracks when exposed to heat or light. Scale that concept to cosmic proportions, and you get a rock that patches itself together like living tissue. But Earth's prototypes require external triggers. This asteroid operates autonomously, suggesting technology far beyond our grasp, or something even more unsettling, that it's not technology at all, but a form of alien biology. Certain extremophiles, like tardigrades, can survive the vacuum of space and repair their own DNA. Could the asteroid be a colossal organism, its mineral body laced with organic repair systems evolved for deep space? Yet the most provocative theory remains robotic probes. The idea isn't new. Scientists like Freeman Dyson once speculated about self-replicating machines, or von Neumann probes, designed to explore the galaxy by copying themselves. If such a probe entered our cosmic neighborhood, its weathered exterior might resemble an ordinary asteroid, disguising its true nature until stress triggers its repair protocols. The Mice Galaxies' violent environment could have damaged it eons ago, leaving it stuck in an endless loop of breakdown and regeneration, a broken machine still following its original programming. Then there's the wild card, exotic matter. Quantum physics allows for particles that remember their positions, a property called topological memory. Could the asteroid's structure be encoded with quantum information, forcing its fragments back into place like a scrambled Rubik's Cube snapping to solve? It's a fringe idea, but in the chaos of colliding galaxies, even the wildest possibilities demand consideration. The implications ripple far beyond this single anomaly. If self-repairing objects exist naturally, our models of asteroid composition need rewriting. If artificial, it suggests intelligence has touched these galaxies before us and left behind artifacts we're only beginning to recognize. Either way, the self-replicating asteroid shatters more than just itself. It cracks open our assumptions about the lifelessness of space, revealing a universe where even rocks might hide secrets beyond our imagination. And in the turbulent depths of the Mice Galaxies, who knows how many other wonders or warnings are waiting to piece themselves together before our eyes. Tucked away in the spiraling chaos of the Mice Galaxies, an anomaly pulses with the entire electromagnetic spectrum at once, a cacophony of wavelengths so complete it renders itself invisible. The hyperspectral anomaly doesn't glow in X-rays, radio waves, or visible light. It blazes in all of them simultaneously, a cosmic static blur that overloads instruments like a microphone held too close to a roaring crowd. Most celestial objects have signatures, preferred frequencies that reveal their nature. Not this one. It screams across every band, a perfect electromagnetic storm with no beginning, no end, and no discernible pattern. At first glance, it resembles noise, the meaningless crackle of the universe's background radiation. But there's a disturbing precision to its chaos. The intensity of each wavelength remains perfectly balanced, like a painter mixing every color into an unwavering shade of white. Natural phenomena don't behave this way. Pulsars have rhythm, quasars have peaks. Even the most violent cosmic events favor certain energies over others. This anomaly shows no preference, emitting gamma rays with the same enthusiasm as microwaves, as if it's deliberately avoiding any signature that might betray its origin. That's where theories diverge. One camp argues for an extreme astrophysical engine, a black hole or neutron star spinning so fast its emissions smear across the spectrum, like a child running their fingers over piano keys to play every note at once. The Mice Galaxies' violent merger could have birthed such an object, its magnetic fields tangled into a knot that churns out chaotic energy. Yet simulations struggle to replicate the anomaly's perfect balance. Nature tends toward imbalance. Maintaining this uniformity would require absurdly fine-tuned conditions. Then there's the transmitter hypothesis. On Earth, spread spectrum communication deliberately broadcasts across multiple frequencies to avoid detection or jamming. Could this be the cosmic equivalent, a beacon designed to be heard by any civilization, regardless of the wavelengths they monitor? The idea isn't as far-fetched as it sounds. A sufficiently advanced society might engineer a signal that blends into the background, visible only to those who know to look for unnatural uniformity amid the chaos. But the most unsettling possibility is that we're witnessing something entirely new, a phenomenon that straddles the line between physics and information. Quantum mechanics suggests that at fundamental scales, particles encode data in their states. Could the anomaly be a cosmic projection of that principle, a region where the universe itself is processing or transmitting information in a language we haven't deciphered? Imagine stumbling upon a radio tower in the wilderness, its purpose clear even if its message remains garbled. The hyperspectral anomaly might be the universe's version of that tower, broadcasting in a code written into the fabric of reality. Or perhaps it's simpler, a flaw in the cosmic canvas. Theories of the holographic universe propose that reality might be a projection from a two-dimensional boundary, like a movie playing on the surface of a bubble. If true, glitches in that projection could manifest as anomalies like this one, places where the underlying code bleeds through, exposing the scaffolding beneath the simulation. The truth remains elusive, but one thing is certain. In the Mice Galaxies, even noise might be a message. Whether it's a natural oddity, an alien handshake, or a crack in reality's facade, the hyperspectral anomaly forces us to reconsider what counts as signal and what we've been dismissing as static all along. In the swirling chaos of the Mice Galaxies, a cosmic contradiction defies the laws of physics, a raging torrent of matter erupting from absolute nothingness, a phenomenon astronomers have tentatively dubbed the paradoxical white hole. Unlike their infamous counterparts, black holes, which devour all that crosses their event horizons, this anomaly vomits forth streams of particles with violent abandon, a cosmic geyser blasting material into the void as if space-time itself has been punctured from within. The concept of white holes isn't new. They've long been the theoretical flip side of black holes, predicted by Einstein's equations as regions where matter can escape but never enter. Yet until now, they've existed only in chalkboard scribbles and thought experiments. This object, however, behaves exactly as a white hole should, if white holes could exist. Energy flares from its core in irregular bursts, ejecting plasma at relativistic speeds without any detectable source. Telescopes have caught the aftermath, glowing arcs of ionized gas stretching light years into space, like the remnants of an explosion frozen in time. But here's the catch: white holes shouldn't exist at all. They violate the second law of thermodynamics, which states that entropy or disorder must always increase. A true white hole would essentially reverse this process, spontaneously assembling order from chaos, like a shattered wine glass reassembling itself midair. That's why most physicists dismiss them as mathematical curiosities, cosmic unicorns too perfect to be real. So what are we really seeing? One explanation lies in the turbulent wake of the galactic collision. When black holes merge, simulations show they can momentarily stretch spacetime into bizarre configurations, creating temporary throats where trapped matter might briefly surge outward before collapsing back in. The Mice Galaxies are a perfect petri dish for such extreme distortions. Their gravitational dance could have warped local physics just enough to mimic a white hole's behavior. Picture a garden hose kinked tightly, then suddenly release. The trapped water gushes out with unusual force, but the hose itself remains intact. Then there's the stranger possibility, a black hole's last gasp. Some models suggest supermassive black holes might eventually exhaust their energy, shedding their event horizons in a final, catastrophic eruption. If true, what we're witnessing could be the death throes of one such titan, a single, spectacular reversal of its eternal hunger before fading into oblivion. Yet the most unsettling theory isn't cosmic, it's cognitive. What if our instruments are simply misreading the data? The jets could be the result of a rare alignment, a pulsar's beam or a quasar's outflow angled perfectly to appear as an eruption from empty space. Alternatively, gravitational lensing might be twisting our view, bending light from distant, unrelated events into the illusion of a single impossible object. The paradoxical white hole challenges more than astrophysics. It forces us to confront the limits of human perception. Are we glimpsing a genuine flaw in nature's rulebook, or is the universe playing tricks on us, dangling riddles we're not yet equipped to solve? In the Mice Galaxies, where reality bends daily, perhaps the most profound truths are the ones that refuse to fit our models, the anomalies that stare back, unblinking, daring us to admit how much we still don't know. Amid the debris of the Mice Galaxies, the dust itself seems alive, particles swirling not at random, but with eerie coordination. The living dust defies the usual aimless drift of cosmic detritus, instead gathering into intricate formations, delicate loops, geometric lattices, even branching patterns resembling fungal mycelium. These structures aren't static, they shift over time, dissolving and reforming as if guided by unseen currents. At first glance, it's easy to dismiss as turbulence sculpted by magnetic fields, yet the precision of these arrangements suggests something far stranger at play. Could these particles harbor the seeds of life itself? The panspermia hypothesis proposes that life's building blocks, amino acids, organic molecules hitch rides on cosmic dust, spreading between worlds like interstellar pollen. The living dust's behavior lends haunting credence to this idea. Spectroscopic analysis reveals traces of complex carbon chains clinging to the particles, some with structures suspiciously reminiscent of Earth's extremophile microbes. It's not proof, but it's a tantalizing hint that these motes might be more than mineral. Imagine a scenario where the Mice Galaxies collision acted like a centrifuge, concentrating organic, rich dust into pockets where electrostatic forces or weak van der Waals interactions allow them to clump with unusual stability. Under the right conditions, could such dust become a nursery for probiotic chemistry? Yet electromagnetism offers a compelling counterpoint. The chaotic merger of the galaxies has woven magnetic fields into knotted braids, creating zones where charged particles might align like iron filings near a magnet. Simulations show that under extreme turbulence, dust grains can self-organize, their slight charges compelling them into transient structures. Some even exhibit rudimentary swarm behavior, a phenomenon observed in lab experiments with ionized particulates. This doesn't require biology, just physics pushed to its limits. The dust's seeming purpose could be an illusion, a side effect of forces we've yet to map fully. But the most provocative possibility lies between these explanations. Certain organic molecules, like polycyclic aromatic hydrocarbons, not only survive in space but can form self-replicating patterns under ultraviolet radiation. The living dust might occupy a gray zone, not alive, not inert, but teetering on the edge of complexity. In the chaos of the Mice Galaxies, where energy and matter collide in novel ways, could we be witnessing a new kind of chemistry, one that blurs the line between the animate and inanimate? As telescopes probe deeper, one truth becomes clear: this dust refuses to be just background noise. Whether it's a cosmic conveyor belt for life's ingredients, a magnetic puppet show, or something entirely unforeseen, it challenges our definitions of what's possible. And in the grand collision unfolding around it, perhaps the most profound discoveries aren't the colossal explosions or glittering stars, but the quiet, deliberate dance of particles too small to see, yet too strange to ignore. At the heart of the Mice Galaxies, a nebula fractures reality itself, not with light or shadow, but with impossible geometry. The holographic nebula doesn't just occupy space, it defies it. From every angle astronomers observe, its gaseous tendrils appear to coil in 3 dimensions, each viewpoint revealing depth, structure, layers. Yet when scientists map its emissions, the data reveals a chilling truth: this cosmic cloud is paper thin. A two-dimensional illusion projecting perfect volume, like a street painting that seems to sink into concrete no matter where you stand. How can a flat structure fool us so completely? The nebula's secret lies in its light. Unlike typical nebulae which glow uniformly, this one's particles emit photons in precise, coordinated patterns. Each molecule acts like a pixel in a cosmic display, angling its light to create parallax effects that mimic depth. It's the same principle behind modern holograms' flat surfaces, engineered to scatter light in ways that trick the brain. But nature doesn't craft holograms, at least not without help. That's where the theories diverge. One camp argues for an extraordinary magnetic lattice woven through the nebula, its fields so finely tuned they align particles like microscopic mirrors. The Mice Galaxies collision could have birthed this phenomenon, twisting magnetism into a natural projector screen. Yet even the most sophisticated simulations struggle to replicate the nebula's perfection. The precision required borders on unimaginable, like a hurricane assembling a Swiss watch. Others whisper a darker possibility: the nebula isn't natural. If the universe is a simulation, a digital construct running on unfathomable hardware, glitches in its rendering engine might produce artifacts like this. Just as video games use tricks to simulate depth without overloading processors, a simulated cosmos could employ optimized holograms to conserve resources. The nebula, then, might be a cosmic shortcut, a patch of space-time where the simulation's resolution drops, revealing the scaffolding beneath reality. But the most unsettling idea bridges both worlds. Quantum physics suggests that at fundamental scales, information about three-dimensional objects might be encoded on two-dimensional surfaces, a principle central to holographic universe theories. If true, this nebula could be a rare macroscopic manifestation of that deeper truth, a place where the universe's underlying code flickers into visibility. The holographic nebula doesn't just challenge our eyes, it questions the very nature of existence. Are we seeing a magnetic marvel, a glitch in the matrix, or a whisper from the universe that reality isn't as solid as it seems? In the Mice Galaxies, even the emptiness between stars holds mirrors, and some reflections are too precise to dismiss as chance. Drifting silently between the spiraling arms of the Mice Galaxies, a frozen relic holds secrets older than time itself. The time capsule comet, a snowball of ancient ice and dust laced with isotopes untouched by the fires of stellar birth. This isn't just another icy wanderer. Locked within its nucleus are atoms forged in the hearts of long-dead stars, preserved for billions of years like a cosmic message in a bottle. When astronomers first analyzed its composition, the data sent shockwaves through the scientific community. Traces of aluminum-26 and calcium-41 isotopes, typically destroyed in the violent cauldron of star formation, lingered in its core, pristine and unaltered. These aren't merely chemicals, they're fragments of the universe's infancy, remnants of a time before our solar system even existed. How could such delicate isotopes survive the chaos of galactic collisions and the heat of newborn stars? The answer lies in the comet's origins. Born in the frigid outskirts of a primordial molecular cloud, it avoided the gravitational turmoil that shaped planets and asteroids, remaining a frozen time capsule drifting in the cosmic deep freeze. Its chemistry suggests it formed in near absolute zero temperatures, far from the radiation and turbulence that would have shattered its fragile isotopes. Think of it as a perfect cosmic icebox, preserving ingredients from the universe's first stellar generations, ingredients that should have vanished eons ago. But the implications stretch far beyond preservation. The presence of these isotopes challenges our estimates of the universe's age and the timeline of galactic evolution. Current models suggest aluminum-26 should have decayed within a few million years of its creation. Finding it intact in this comet implies either our understanding of half-lives is incomplete, or this material originated in an environment so cold and shielded that decay rates were altered. a concept that bends the rules of nuclear physics. Some theorists even speculate the comet might carry matter from beyond our galaxy, hurled into the Mice Galaxies during a long-ago intergalactic collision. Then there's the tantalizing possibility of pre-solar chemistry. The comet's dust grains, examined under spectrometry, show crystalline structures unlike anything formed in our solar system. Their intricate patterns suggest they condensed slowly, in the quiet darkness between stars, where temperatures and pressures allowed for perfection unseen in our own asteroid belt. If true, these grains could be the universe's original building blocks, the raw materials that seeded not just planets, but perhaps life itself. The time capsule comet doesn't just offer a window into the past, it rewrites the story of our cosmic neighborhood. Every molecule in its frozen heart whispers secrets about where we came from, what existed before us, and how rare or common our corner of the universe might be. And as it continues its lonely journey through the Mice Galaxies, one thing becomes clear. Some of the universe's greatest truths aren't written in the blazing light of stars, but in the silent, frozen depths of the smallest wanderers. Among the wreckage of the Mice Galaxies collision, a small cosmic anomaly beats like a distant drum, the resonant dwarf galaxy. Unlike most galaxies where stars are born and die in chaotic bursts, this tiny stellar collective pulses with eerie synchronicity. Every 11 million years, like clockwork, a wave of supernova erupts across its span, followed immediately by a surge of new star formation, as if the galaxy itself is breathing, inhaling the ashes of the dead to exhale fresh light. This rhythm defies all known models of galactic evolution. Dwarf galaxies are typically messy, their stars aging unpredictably under the whims of local conditions. But here, stellar life cycles align with precision, orchestrated by forces we're only beginning to unravel. The secret might lie in gravity's unseen symphony. The Mice Galaxies collision has woven a complex web of tidal forces through this region, stretching and compressing gas clouds in regular intervals. Picture a pendulum swinging through molasses. The surrounding chaos slows its motion but can't stop its rhythm. The dwarf galaxy, caught in this cosmic metronome, may be resonating with those gravitational waves, its star-forming regions squeezed and released like an accordion playing the same refrain over eons. Yet there's a stranger possibility: external tuning. Some theorists suggest the synchronization isn't natural at all, but the result of deliberate manipulation. Imagine a civilization advanced enough to harness galactic-scale energies. Perhaps they've positioned black holes or dark matter filaments as tuning forks, vibrating the dwarf galaxy's gas clouds into harmonic alignment. Far-fetched perhaps, but nature rarely produces such perfect cadence without help. Even if artificial influence isn't at play, the galaxy's behavior hints at undiscovered physics. A gravitational feedback loop where dying stars trigger their successors with uncanny efficiency. Then there's the music of the spheres made literal. Spectral analysis reveals that the galaxy's pulsations produce gravitational waves at frequencies that, if converted to sound, would form a perfect a tone found in everything from Earth's thunderstorms to the resonance of Saturn's rings. Coincidence or evidence of a deeper universal harmony we've yet to decode? The resonant dwarf galaxy doesn't just challenge our understanding of stellar life cycles. It whispers that the universe might be more orchestrated, more musical than we ever dared to dream. As telescopes continue monitoring its rhythmic dance, one truth becomes undeniable in the chaos of colliding galaxies. Even the smallest structures can hold the grandest secrets. Whether shaped by unseen forces, alien engineering, or the universe's own hidden melodies, this tiny galaxy pulses with questions we're only beginning to hear. And in its heartbeat, we might finally find the rhythm of creation itself. In the swirling debris of the Mice Galaxies, a cosmic dagger hangs suspended, a filament of pure darkness skewering the luminous wreckage of colliding star systems. Astronomers call it the cosmic thorn, a needle-like structure detected not by light, but by the way it warps the fabric of space around it. This isn't just another dark matter clump. It's a razor-thin spike stretching nearly half a light-year in length, its presence revealed only through the subtle distortion of background starlight, a phenomenon called gravitational shear. Where ordinary dark matter halos blur like ink in water, this anomaly pierces with surgical precision, its edges sharp enough to split galaxies. Dark matter's nature has long eluded scientists. We know it outweighs visible matter 5-to-1, binding galaxies together with its gravitational embrace, yet it remains ghostly, detectable only through its pull on the cosmos. The cosmic thorn changes the game. Its needle-like form suggests dark matter isn't just a shapeless fog, it might have structure, texture, even architecture. Imagine a material that doesn't interact with light, yet under certain conditions, folds itself into filaments as precise as scalpel blades. The thorn's gravitational shear patterns hint at densities far exceeding typical dark matter halos, as if its particles have aligned into a cosmic fiber optic cable, channeling gravity along its length. What could forge such an unnatural shape? One theory points to the galactic collision's shockwaves. As the Mice Galaxies tangled, their dark matter components might have been stretched and compressed, triggering phase transitions akin to water freezing into ice. Under these extreme conditions, dark matter's hypothetical particles, whether WIMP, actions, or something unnamed, could have crystallized into this needle-like formation. Alternatively, the thorn might be a fossil relic from the early universe, a scar left when dark matter first decoupled from normal matter, its particles knitting together into primordial threads that still lace the cosmos today. Then there's the unsettling possibility of dark matter weather. Just as Earth's atmosphere sculpts ice into jagged spires, some models suggest galactic magnetic fields. Though dark matter shouldn't feel them, might influence its distribution through undiscovered interactions. If true, the thorn could be a shadowy stalactite, grown over eons in the invisible currents between galaxies. But the most profound implication lies in the thorn's very existence. If dark matter can take ordered forms, it might build unseen frameworks beneath the universe's visible layers. Galaxies could be strung along filaments like dew on a spider's web, their motion dictated by scaffolds we've only just begun to glimpse. The cosmic thorn doesn't just pierce gas and stars, it punctures our assumptions, revealing a cosmos far more structured and far stranger than we ever imagined. And if such spines are common, woven through the cosmic tapestry, what else might be hiding in plain sight, invisible, knife-edged, and waiting to be found? In the Mice Galaxies, even the darkness has teeth. The final mystery of the Mice Galaxies might be its most unsettling, a stark, flawless circle of metal orbiting a lonely star like a cosmic wedding band. The engineered ring defies every law of celestial mechanics, its surface too smooth, its orbit too precise, its composition too pure to be the work of nature. Unlike the chaotic debris fields left by colliding galaxies, this structure gleams with unnatural perfection, reflecting starlight in unbroken arcs that make even the most skeptical astronomers pause. How does something like this form? Natural rings like Saturn's iconic loops are born from dust and ice, sculpted by gravity into delicate but imperfect spirals. The engineered ring, however, consists of refined metallic alloys, their atomic structures arranged with precision found only in laboratories. Spectroscopy reveals traces of neodymium, titanium, and an unknown composite resembling graphene, but with conductivity far exceeding any known material. This isn't the result of a supernova's forge or a neutron star's crushing pressure. It's the footprint of deliberate craftsmanship. Theories spiral into the extraordinary. The most grounded explanation suggests a Dyson ring, a fragment of what was once a megastructure designed to encircle a star and harness its energy. Imagine a civilization so advanced they built a skeletal framework around their sun, only for the Mice Galaxies collision to shatter it, leaving this single, intact segment drifting through the wreckage. If true, it would mean we're staring at the ruins of engineering dwarfing anything humanity has conceived. But darker alternatives whisper at the edges of plausibility. Could this be a beacon? Rings are mathematically efficient for broadcasting signals across interstellar distances, their curvature focusing electromagnetic waves into tight beams detectable light years away. The ring's composition might even hold clues its unknown alloy could be a superconducting medium, ideal for transmitting messages we haven't thought to listen for. Then there's the chilling simplicity. What if it's art? Ancient human cultures buried treasures with their dead, sending artifacts into the unknown as offerings or declarations. If another civilization faced extinction during the galactic collision, this ring might be their monument, a final "we were here" etched in metal rather than stone. The engineered ring doesn't just challenge our understanding of the cosmos. It forces us to confront the possibility that we're not the first to reach for the stars. And in the silence of its orbit, one question lingers. If this is a remnant, what else might be waiting in the dark? From dancing black holes to hollow planetoids, from self-healing asteroids to a nebula that exists in 2 dimensions yet tricks our eyes into seeing 3. The Mice Galaxies have shown us a universe that refuses to play by the rules. These 30 cosmic anomalies don't just challenge our textbooks, they rip them apart, proving that reality is far stranger than our boldest theories predicted. Who could have imagined a magnetar that sings in harmonic scales, or a comet carrying isotopes from the dawn of time? What kind of physics allows a galaxy to pulse with the regularity of a heartbeat, or dark matter to crystallize into a needle sharp enough to pierce space-time itself? Each discovery here feels like stumbling upon a locked door in a house we thought we knew. Every key we try only reveals another corridor of questions. The bioluminescent gas cloud mimics living light. The fractal galaxy fragment whispers of mathematical perfection woven into chaos. The engineered ring stands as either a monument or a message, its polished surface reflecting not just starlight, but the haunting possibility that we might not be the first to search the skies. So what does it all mean? Are these objects cosmic coincidences, natural phenomena pushed to their extremes by the Mice Galaxies' violent dance? Or could some of them, just maybe, be signatures of something more? The universe has never been shy about surprising us, but this collision has concentrated its weirdest wonders into a single, shimmering puzzle box. Now it's your turn. Which of these 30 mysteries left you utterly breathless? The hyperspectral anomaly blaring static across every wavelength, the vanishing quasar that erased itself from existence. Drop your favorites in the comments, and if you're craving more deep dives into the cosmos's greatest riddles, hit subscribe so you never miss an exploration. Because here's the final, thrilling twist. The Mice Galaxies are just one collision in a universe brimming with enigmas. Every time we think we've seen it all, the cosmos winks back with another impossibility. So tell me, when you look at these celestial rebels, do you see nature's boundless creativity, or something even more extraordinary? Could these objects be proof we're not alone, or is the universe simply weirder than we ever dared to imagine? The answer, like the galaxies themselves, is still spiraling toward us, and the next revelation might be closer than we think.